All right, this is Tuesday, April 13th, 2021, Physics CP Period 2, and I'm going to cover some of the same material I did yesterday that was recorded, but maybe add the equation correctly this time, and maybe not quite exactly just yesterday's material. But first, here's a kind of an outline of what the district pacing guide is saying I should try to touch on during this last quarter of our school year. And it's not exactly what the pacing guide said. It's also a blending of what I normally cover when we study the entire universe. And it's not in a great order, but it's something. So, yesterday I talked extensively about the age of the Earth. And I'm going to revisit that today a little bit uh, with the correct formula that I didn't actually use yesterday, maybe a couple examples. And from there, the logic goes like this. If we can establish some estimate about the age of the Earth, then logically we would expect that the sun and the other planets and the rest of the universe are at least as old as the Earth, right? We would like to think that the Earth is younger than the rest of the universe, or at the same age, but not older. Olber's paradox is just the name of some guy in the 1800s who posed the question, why is the nighttime sky dark? And working out a reasonable answer to that tells us something about our universe. Doppler is the name of some French scientist, also from the 1800s, and he did some investigations with a trumpet player on a train and developed a formula that predicts the compression or stretching of transverse waves as different effects, motions take place. So Mr. Monsieur Doppler worked out a formula that lets us calculate how fast something is coming towards us or moving away from us based on our observations of the light that we see coming from it. Edwin Hubble is an astronomer who studied galaxies in the 1920s, maybe, and maybe 1930s, using the Mount Wilson Observatory. You can actually see it from our classroom campus if you look on top of the mountains. There's a little white bump up there. That's the observatory dome. And while he was up there, he made a discovery that we call Hubble's Law. Then there's the cosmic microwave background. And Penzias and Wilson are a couple researchers who were trying to solve a problem involving cell phones. And they made this observation, and it turned out to be a big deal because it matched a prediction that was made before they began their troubleshooting. It'd be great to reteach you a little bit about the periodic table and what is the universe made out of? So, uh, so far written, that's not hypo, it's actually hydrogen, colon, helium, colon, dot, dot, dot. So it's not high he or hypo. How are the heavier elements formed? And so there's a term called nucleosynthesis, the star cycle, the lives and deaths of stars. There's actually a radio play, I hope we do. Spectral analysis, oh man, it sounds like a science term. It is. And for the two of you or so who are coming to my classroom, I'll try to hand you a spectroscope and have you observe with your own eyes spectral lines of different substances. HR is not human resources at all. It is Hertzsprung Russell, the name of two other guys and they each pretty much simultaneously and independently worked out a very useful diagram that uh, allowed us to understand the life cycles of stars. So you will become masters of at least observing the diagram and interpreting what you see on it. All right, so that's some of what I want you to learn about. Uh, but I began yesterday with the age of the Earth. And the story that I was telling yesterday was about um, there being a religious question about the age of the Earth. So there is the Bible. And in the Bible, it says God created the heavens and the earth, and he did this, and then, there was light, and this was good, and then he did this, and he did that, and on the seventh day, he rested. Okay, great. And then later on, in the book of Genesis, I suppose, he created Adam, and after a while decided, well, Adam could really use a companion, so then he created Eve, and human life goes on from there. They had a couple of kids, Cain and Abel. I think one killed the other. One of them had kids, and one of them had kids, and one of them had kids. And so this uh, parishioner, okay, someone who is religious, went to her bishop, and he was a smart young guy, and asked him, "How old is the earth?" And so what this bishop did, and it's actually USSHER, Usher, what he did is he tallied up all the information he could find in the Bible, and it said some um, hmm, hmm, things that would challenge our current beliefs if it weren't written in the Bible. It says, okay, so like Adam lived about 930 years or so, and then he had his first child when he was about 130 years old, and Methuselah. Okay, I don't quite remember the numbers, but the point is, they weren't just 40-year-old people or 60-year-old people when they died. In the Bible, some of these people lived, I think one guy lived over 900 years, Methuselah, something like that. So the first few generations of human life, according to the Bible, had vastly longer lifespans than our current generations. Anyways, so he tallied it up, and eventually he worked his way through historical events in the Bible, and then found a matching reference in Greek or Roman history, recorded history, and so that let him fix a date. And from all of that, he worked it out and established and told this woman, okay, well, and this was, I think, in the 1600s he did this. I forget exactly when he lived and died. But he decided from his research and calculations that the entire universe, the Earth, was created in the year 4004 before Christ. And believing that God likes to work on one of four special days of the year, either the equinox or the solstice. So either on the first day of spring, or the first day of summer, or the first day of fall, or the first day of winter. Uh, and reading in the Bible that when Adam and Eve were first created, there was plenty of ripe fruit available for them to eat, which of course led to the problem of Eve eating the forbidden fruit. But from that, Bishop Usher concluded it must have been fall time. And so, therefore, he selected the first day of fall from the year 4004 BC. Now, our calendars have shifted over the centuries. So, it didn't occur on September 21st like it does in current times. Back then, it would have occurred on October 23rd. So, he not only fixed what year the Earth was created, but what day of the year the Earth was created. And he even took it one little teeny tiny step further and said, "Oh, it it was formed, I think, near the end of the day is how he decided it went, and so that meant like 9 p.m. or something in his interpreted. Anyways, he set the time and the day and the year that the universe was formed, according to the Bible. Well, well, yesterday I talked about how things evolve over time, and the example I used was a bicycle. And the very first bicycles, if you look at an old wood carving from Europe, basically it was two wheels and you straddle it and your feet are walking on the ground and the bar between the wheels is supporting some of your weight. And that was basically the first bicycles. Well, they've evolved over time and various interesting shapes. And now we have bicycles that are mm, quite advanced compared to the original ones, right? So we have multi-speed bikes. We have them with little coverings you can put over them to reduce wind resistance. We have them where you lean way back in the chair. Oh gosh. And I'm not even talking about electric bikes, right? Just mechanical bicycles, human powered. Same thing for the laptop or computer screens you're using right now. Heck, when I was a tiny tot, flat screen televisions did not exist, right? Even when I was just your age. Uh, my television viewing began with black and white television, and eventually color came along, and then eventually uh, digital TVs came along, and then eventually flat screen TVs, and it's still evolving. The same thing can be said even about, I don't know, a pen, right? So pens used to be quills dipped in inkwells. My mom used to collect those things, and now we have pens that have been designed to work in outer space. Um, Normally, a pen won't work in outer space because there's no gravitational pull to draw the ink down to the bottom of the pen. And what happens when you want to write upside down? So, U.S. government hired the Fisher Pen Company to develop a pen that would write even in the weightlessness of free fall in orbit around the Earth or on the way to the moon. The Soviet Union solved the same problem by just using a pencil. So different solutions, but evolution nonetheless. Okay, so out of all this, you can see from yesterday I wrote the word how here and the word why over there. And the point I want to emphasize that I made yesterday is that science is really trying to understand how the universe works. And religion is really trying to address why you exist. Why are you here? You know, what was, if you believe in God, what was God's purpose in creating you specifically? These are two different questions, and they're not in conflict with each other. From the view of a scientist, we would say what the Bishop of Usher did was a very meticulous, thorough work working through the Bible. But the Bible is more like a guidance document for why you should aspire to do, develop your talents for good as opposed to for evil. Okay. And the technical understanding of the universe thousands of years ago, as the Bible was being written, couldn't support a technical language. Even when I was born, DNA was hardly discovered as being genetic code, right? So now we can tell you all about it, and we use gene manipulation and a lot of technology understanding to develop a vaccine against a virus in just 1 year of time. Well, thousands of years ago, the whole idea of DNA had not yet evolved in human understanding. So, how do you explain to people who don't have any kind of technical language the age of the universe? And so, the Bible addresses these questions to satisfy the parishioners who are curious about it in the context of, gee, what does the Bible or other religious source, whichever one you want to pertain to. So if you are Islam, what does that religion say about the age of the universe? If you're Buddhist, what does that religion say about the age of the universe? So pick your religion. I'm just more familiar with Catholics. So the religious world wouldn't even have the language tools to explain the age of the universe in any way other than perhaps the way that the Bishop of Usher went about answering that question. So, from the point of view of a scientist, we don't literally take this to be the answer. Instead, what we try to do is observe nature and develop models, mostly mathematical models, that allow us to predict the behavior of nature as we observe it. And from that, develop theories that match the models. And we're always challenging it and checking ourselves and revisiting our beliefs, right? So, for the age of the earth, from a scientific point of view, you can only remember back to your early childhood at best. And after that, actually, how do you even know that yesterday existed, right? Maybe today is the first day of existence for the entire universe, and everything before today is just false memories that were planted in your head. So there, you could choose to believe that, or you could choose to be convinced that no, life has been continuous since at least since you were born, as far back as you can remember. And then you have to kind of rely on trusting that your parents existed before you did, and that their memories are valid, and their grandparents. And okay, so and then you need to trust written human history for a while. So written human history doesn't go back far enough, we think. The oldest written human history doesn't say, oh, on this morning, uh, the universe was formed, right? Well, in the Bible, yes, but in outside of religious documents, no. So outside of religious documents, what do we have? We have trees, for example. Trees grow and die, and every year that they grow, they form a new ring, a growth ring. You could core the tree and count the rings, and uh, each ring represents 1 year of life of the tree, and from that you can establish the age of the tree. The state of California happens to have the oldest living land organisms on the planet. The bristlecone pine forest up near Bishop, California. And there are a couple other places in the United States, but California is where the largest tree grove is, and they are over 2,000 years old. Now, those are the living trees. A tree that lived before this one and died, well, okay, so it doesn't have tree rings increasing anymore, but now here's another trick. The pattern of the growth rings depends on the climate and the weather each year. On a good year, you've got maybe thicker rings. On a drought type year, you have thinner rings. So there's a pattern that shows up from year to year. And if you look at a dead tree, maybe you can make a match that says, oh, the last 10 years of life for this dead tree overlap the first 10 years of life of this living tree. And so now, if this tree lived for 1,000 years and this tree is 2,300 years old, well, great. Now you can extend the age of the earth back um, an additional 1,000 years. And maybe you can find several generations of trees that take you back like this. So there's one technique for trying to figure out the age of the earth. The other techniques that work well are in your reading. I think they called one of them Verve, or I forget the word, but it starts with V. It's in your homework assignment, and it refers to the pattern of sediments accumulating in lakes. So, on a given year, just like growth rings in a tree, there are sediment patterns that accumulate based on how much water is flowing and da da da. Well, we don't think that the universe formed with trees present at the beginning of the universe. We believe that the universe formed a long time ago and that conditions slowly changed over time, and that eventually life was created somewhere in the universe, maybe only on Earth, maybe somewhere else first, and then came here. And over more time, the life forms evolved on this planet. We can look at fossils and observe that horses, for example, used to be small little critters, maybe knee high, I think, something like that. And over time, they became larger to the way they are today. Uh, there are fossils of animals that no longer exist, like the American lion and dinosaurs, of course. So, figuring out the age of the Earth is not a trivial thing. I'm going to pause the video right there. All right, our 3 minute break is over, and I want to move on a little bit and talk about absolute dating of the age of the Earth, not anything else. So there are a couple of things, and it's going to be in your reading. One is called relative dating, and that means when you look at something, particularly rocks or trees, for that matter, relative dating means the innermost ring is I suppose it's the oldest ring, and the outermost ring is the youngest ring. I think that's how it works. Of course, it could be, yeah, that's probably the way it works. But for rocks, at least this one I have correct. Yesterday I drew a mountain and then an ocean, and here's the shore. And yesterday I mentioned we believe that erosion, every time it rains and the wind blows, erosion causes the mountains to crumble and flow and accumulate in the ocean. And we believed that for the longest time that you would find the oldest rocks on the Earth at the bottom of our oceans because they would have come from old mountains that are, you know, gone, just hills. Turns out, if we get to study this, the youngest rocks on the Earth are found in the oceans. Complete surprise. And that discovery didn't come about until less than 100 years ago. But what I do want to explain about rocks is that we classify them into three general categories. So there's igneous rock, which means it is molten and cools down. So lava, basalt, okay, uh, hot rocks that cool down. Then there is metamorphic rock, and that is rock that has been partially melted to where it became sort of like taffy, and you could bend it and squeeze it. So under enough heat and pressure, it partially uh, melted, but not enough to become like lava again or magma. Lava is magma on the surface. And finally, there's sedimentary rock. And this is what you see mostly when you look around you. When I went camping, saw lots of sedimentary rock. And that is where rock is deposited through the action of wind and or water into layers. And relative dating says, well, the bottom layer is the oldest layer, and the top layer is the youngest layer. So that's relative dating. You can say, oh, this is middle in age between that one and that one. But you can't say, oh, this is 5 years old, or this is 5 million years old, or 500 million years ago. Okay, we don't know. So relative dating is just this type of arrangement of information. But if we want to figure out the age of the Earth, we really need to deal with absolute dating. And that means, okay, I have this tree, I see it's alive today, I core it, I count its rings, I see this tree is 15 years old. And, I planted trees in my youth. We could go core them today and say, oh, yeah, that's right. I remember planting it in the year, da, 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 da. Okay, so absolute dating. One of the big tools for life forms on Earth is carbon. All life on Earth is based on carbon, and carbon has different isotopes. You may remember that carbon has 6 protons, and there's an isotope of carbon that only has 6 neutrons. So up here, superscript top left, is the mass number, which is the sum of the number of protons plus the number of neutrons, carbon 12. There also exists an isotope of carbon called carbon 14. And carbon 14 is radioactive. Yikes. Yesterday I said you breathe it in the air. Well, this morning I asked Lord Google about that, and the internet said, well, that's not exactly how it happens. We have the Earth, we have the Earth's atmosphere, we have bombardment of our atmosphere by cosmic rays and gamma rays, and that creates carbon 14, radioactive carbon, in our atmosphere. And then instead of breathing it in directly, it apparently is taken in by plants. And the plants absorb or ingest or take in carbon 14, and then animals eat the plants. We eat plants and other animals, so we're omnivores. And going up the food chain, whatever animals we eat, maybe they ate animals, but those animals ate plants. I mean, it always comes back to animals eating plants somewhere down the food chain. As long as you're alive and you're eating, you are ingesting radioactive carbon, carbon 14. When you die, you stop eating. And radioactive carbon decays. It so radioactive materials decay over time. You have a parent and it decays to a daughter. I don't even care what the daughter is for carbon 14. What I do want to tell you is that it has a half life of 5,730 years. Ta da! Yesterday I mixed the numbers up, but there it is. And yesterday I didn't give the formula. Here it is. The amount of the original substance that you have at a given time is the amount of substance that you originally had times 1/2 raised to the amount of time that has gone by, but divide that by the half-life time for that particular radioactive substance. Okay, so here's a formula, and I think you have some homework related to this. So, what it says in simple words is that if you start with 100 grams of carbon 14, then after 5,730 years, you're only going to have 50 grams of carbon 14. And after another 5,730 years, no, it's not all gone. Only half of what's left disintegrates. That's why it's called a half life. And so now you're down to 25 grams. And then another 5,730 years go by. And now you're down to half of 25, which is something like 12.5 grams. And it gets harder and harder to measure these tiny fractions of the total. So there's a limit to how far you can use this technique, but it works well on the assumption that the rate at which carbon 14 is being produced in our atmosphere is presumed to be constant. The rate at which it's being incorporated into life on Earth is presumed to be a constant. And as long as that's all true, this is a technique that we can use for absolute dating and saying, oh, this tree, we can use this technique and say, oh, that tree actually died in uh, 10,000 years ago, okay, 20,000 years ago. In fact, this technique works out to, I think, 70,000 years back in time. We can date the age of of dead material on Earth, formerly living carbon-based life on Earth, an antler, a horn, a piece of cloth, a a moccasin, a, a leftover Twinkie. Okay, uh, well, organic material, anyways. Maybe not the Twinkie, but the hamburger. Okay, so we can date life on Earth back at least 70,000 years. Charcoal from campfires, for example. Beyond that, there are other radioactive materials. And the best ones for our techniques are potassium, and I'm going to use the chemical symbol K for potassium, as the parent, and argon as the daughter. So potassium argon. Great. Apparently, its half life is 1 comma 248 comma 000 comma 000 years. 1.248 billion years is the half life for potassium argon. And that's great because this means rocks are clocks. Potassium is found in some minerals, so this doesn't work for every type of rock. It only has to be, it only works for the rocks that have potassium in their mineral content. And we presume that the minerals are formed at the same time the rock is formed. And the argon is a noble gas. It's the daughter. As long as it can't escape from the rock, we've got a way of establishing the ratio of daughter to parent, and it's that ratio that allows us to determine the age. So let's do an example. I have, let's do with carbon 14. So we have smaller numbers. I have a sample, and the sample is 82% carbon 14. Okay, so right away I can tell you, well, that's between 100% and 50%. So it's going to be less than 5,730 years old. Now, the formula will let us figure out what its age actually is. So if I take this formula and say, at this time, I have 82% of what I started with, and write that as a decimal, I would say 0.82 equals 0.5, because that's 1/2 in decimal form, raised to, I'm just going to call this x for right now. We need to solve for x. All right, x is going to be the ratio of its actual age to its half-life. And I don't remember how to solve for x. So I'm going to pause and ask you students to explain to me from math class, how do I solve for x? Okay, the students suggest I take the log of base 5 of both sides. Wow, the log base 5 of 0.82, set that equal to the log of base 5 of 0.5 to the x power. And I vaguely remember that the x would go in front of here. So this would be equal to x times the log of base 5 of 0.5. So if I divide both sides by the log to base 5 of 0.5, that should tell me that x is equal to the log to base 5 of 0.82 divided by log to base 5 of 0.5. Huh. Well, I do have a calculator. I'm not entirely sure. Okay, so while I sit here staring at this, my students have made a couple of improvement suggestions on how to do this problem as opposed to doing it this way. So one suggestion was to take the natural log of 0.82 and the natural log of 0.5 to the x power. And it seems like that would be equal to x times the natural log of 0.5, and that therefore x would be equal to the natural log of 0.82 divided by the natural log of 0.5. And if I try that, natural log of 0.82 divided by the natural log of 0.5. Well, at least there's a way we'll be able to check our answer afterwards. So this says x is equal to 0.2863. Let's do it to force it. And this x is the ratio of how much time has gone by divided by the half-life time. So the amount of time that has gone by would be equal to 0.2863 times the half-life time, which is 5,730 years. So if I multiply this result by 5730, it says the amount of time that has gone by is 1,640 years. And therefore, in this example, that would be how many years in the past the sample stopped eating, the sample died. It seems like a totally reasonable answer to me because we wanted something that was less than 5,730 years old. And it's mathematically simple enough to just plug that into the original equation and confirm that we come out with 85%. So if we start with 100% today, and we multiply that by 1/2, raised to the 1640 divided by 5730 power, we expect to get 82% or 0.82 on a calculator. So let's confirm that. So 100 times 0.5 raised to the open parentheses 1640 divided by 5730 close parentheses. Oh man, what are we going to get when I press the enter key? Oh man, we're hoping it becomes 0.82. It's autofocusing, autofocus, and 82%. Yes. Okay. So you students correctly taught me how to do this problem. Nice. Whew. Okay. So this math approach worked best. We're using the property of natural logs that says the natural log of something to the x power is x times the natural log of that term. Okay, good, because I think on your homework you might have some calculations like this. So let's get to the punchline. The punchline is we have been able to date rocks on the surface of the Earth that are 3.2 billion years old. And from this, we conjecture that the universe is at least as old as the Earth. The sun is at least as old as the Earth. And human written history is only like, 7,000 years old. I forget the number. So if I were to write this out, 3,200,000, that's only 3 million. So add 3 more zeros, and this is the age of the oldest rocks on the surface of the Earth that we can date by the potassium argon method. Now, we don't think that this is the age of the Earth. We have reason to believe that the Earth is even older than this. But look at human history. If it's only 7,000 years of written history, you know, this doesn't help us at all in establishing the age of the Earth and the age of the universe. So, written history, the invention of language. And I think there's been a fine PBS special about the origins of language, and it starts off with this with these hieroglyphic type symbols, maybe. No, farther back than that. I forget the culture, but okay. Written language doesn't help us in our belief as to what the true age is of the Earth and the universe. Now, the next thing I listed on this little handout here was the sun. And right away, we have a problem with our understanding of the sun. The very first lecture I gave you students about the universe dealt with the Greeks. And just to recap it, because there's only 5 minutes left in the period, Aristarchus figured that if the moon goes around the Earth at a constant speed and in a perfect circle, he counted the number of days from first quarter moon to third quarter moon, and the number of days from third quarter moon to first quarter moon, figured they were different by 1 day, and based on that, established that the sun must be 50 times farther away from the Earth than the moon is, at least, right? At least 50 times farther away. And because when we look up in the sky, the size of the sun and the size of the moon appear to be the same size, that the sun must be at least 50 times bigger than the moon. Okay, well, another Greek guy, or actually Aristarchus as well, established that based on the size of Earth's shadow on the moon being 7/3 the size of the moon, the sun being 50 times bigger than the moon, he worked out the geometry that said the Earth, the Earth here, sorry, the Earth is bigger than the moon and smaller than the sun. Great. And another guy using a well that was dug and information in the Library of Alexandria in Egypt established the size of the Earth. And knowing the size of the Earth, they could work out the distance to the moon, the size of the moon, the distance to the sun, the size of the sun. So now this brings us to the next problem in understanding the universe. If the Earth is at least thousands of years old, according to written history, and billions, according to modern radiometric dating, we believe for all that time that the sun has been shining. We believe the sun has been shining for at least as long as the Earth has existed. Maybe not as long as the universe, but at least as long as the Earth has existed, there's been a sun. So around the 1700s or so, the question came up, what makes the sun shine? On Earth, before the discovery of electrical devices, the invention of the light bulb, the only source of light and heat on the Earth was by burning things. And one of the best sources of light and heat that we had to work with is coal. So a scientist did a calculation that said, we know the distance from the Earth to the sun. We can measure how much heat and light is put out by the sun every second of time. That we measure in a cup here on the surface of the Earth. Well, in fact, used to be an activity that we did. We did this last year. We took a little styrofoam cup, cut a 1 centimeter diameter hole in the top of the cup, put in some water, measured the initial temperature of the water, took it outdoors, let it sit in bright sunlight for 15 or 20 minutes, measured the final temperature of the water, and assuming that all the heat and light that heated the water only came through the 1 centimeter square opening, calculated what is the energy output of the sun on that one little centimeter area at the distance of the Earth from the sun. And then use the formula for the area of a sphere and say, okay, what is the total energy across the entire sphere surrounding the sun of the distance of the Earth from the sun? If one little tiny centimeter is, let's say, 1 watt, what is the energy of the sun? The period has just ended, so I'm not going to finish the story. To be continued.